Hello everyone, a very good morning to all of you. Let me begin by introducing myself. I am Mr. Manoj Nikam, a research scholar from VGTI Matunga. I am presently doing my research in the field of microtexturing, and this paper is related to the effect of microtexturing in reducing cutting forces and cutting tool vibrations in single point tungsten carbide cutting tool. Dr. Sachin Mastut sir and Dr. Tribeni Roy sir are mentors who guided me in this research. The primary objective of this study was to analyze the effect of microtextures during the orthogonal cutting of AISI 1018 mild steel. As can be seen in this image, the study began by fabricating the circular microdimples on the insert by Ytterbium laser. The texture tool was used for turning a mild steel workpiece under the continuous lubrication condition. The post-machining effects were studied under the ACM and an optical microscope. The display table shows a summary of some of the notable scientific material referred to while conducting literature survey. As can be observed, among the most research findings, cutting tools with microtextures on cutting face have shown notable improvement in reduction of wear, cutting forces, and friction. However, these benefits are entirely depends on the various parameters like width, depth, pitch, distance from the tool edge, etc. considered for the microtextures. I have listed the outcomes of some of the studies here. As can be seen, texturing helps reduce the resultant friction and wear generated, thereby extending the operational life of a tool. The machining forces were found to be less impactful on texture tool as compared to a non-texture tool. As can be observed, we have predefined the cutting conditions like cutting velocity, depth of cut, feed rate, etc. By means of Taguchi L27 orthogonal array, the impact of microtexture features like dimple size, pitch, depth and distance between the textures and cutting edge, also called DFE, have been analyzed to determine the optimum performance of a cutting tool. In this slide, I have shown the equipment used for experimenting. We use cutting tool made up of non-coated and coated tungsten carbide. The manufacturer is Idea and the model is carbide turning insert CNMA 120404 grade CJ215K and THA. The cutting tool has a plain rake face without a chip breaker, a characteristic deliberately selected to its texturing on the tool and to examine the effects of individual texture parameter. The schematic of tool and its arrangement in the tool holder is shown in the schematic diagram. As I said before, microtextures were imparted on the rake surface of coated and non-coated tungsten carbide cutting tools by using Ytterbium laser. Micro-cavities of circular shape were machined on tool surface. Circular shape micro-cavities were selected as they are axisymmetric and not impacted by the flow direction of the chip, unlike triangular and rectangular micro-cavities. Arrangement of dimples on the cutting tool and their size are key factors, as the optimum configuration of these features will result in maximum efficiency of the texturing effect during the cutting process. Hence, Three texture parameters were selected, namely dimple diameter, pitch, and the distance from the edge of the cutting tool. The image on this slide shows the profile of the circular microdimple surface and the distribution of the microdimples over the cutting tool. The parameter pitch defines the smallest distance between the centers of the two neighboring microdimples. The distance between the bordering array of dimples and the cutting edge must be optimized, as textures extremely close to the cutting edge will obstruct the cutting process and also reduce the strength of the cutting edge. On the contrary, if the textures are located very far from the cutting edge, it will reduce the efficiency of the textures. In this slide, figure A shows the experimental setup used for conducting orthogonal cutting. To measure cutting tool vibrations, we have used a 3-axis digital accelerometer. The cutting forces generated have been measured using a dynamometer. Figure B shows a magnified schematic of texture cutting tool. To measure vibrations of cutting tool during machining, a triaxial accelerometer was mounted on the cutting tool holder, which in turn was connected to a data acquisition system. Basically, an accelerometer is an electromechanical sensor which calculates the forces of acceleration due to gravity in G unit, that is gravitational constant G, where 1G is 9.81 meter per second square. The ADXL335 variant measures the acceleration along X, Y and Z axis to give an analog voltage output, which is directly proportional to the acceleration along the 3 axes. The accelerometer output had been connected to microcontroller, which can process output voltage by converting them to digital signal using analog to digital converter. The cutting forces derived from the multiple experiments conducted on various combinations of the texture tool are plotted in this slide. In the non-coated tool used for experiment number 27, the cutting forces were reduced by 81.59%. Microdimple parameters, namely distance from the edge, pitch and dimple diameter, were found to have 31%, 46% and 22% contribution toward the frictional forces respectively. This slide shows the resultant wear on the tool after machining. Wear is observed along the edge of the tool nodes exactly at the point where the workpiece and the cutting insert meet. The wear is higher in non-texture cutting tool seen in figure C as compared to figure A and figure B. This is due to higher concentration of cutting forces, cutting vibration, point friction and localizing. As I mentioned before, a triaxial accelerometer ADXL335 was mounted near the contact on the tool holder shaft which held the cutting tool insert. It was noted that most of the texture contacts with 80 micrometer distance from the edge and having 100 micrometer pitch generated low magnitude vibration compared to non-texture surfaces. This happened due to the improved bonding of lubricant on the textured surfaces. Figure depicts the mean effect plot charted to estimate the texture parameter majorly influencing the resultant cutting force. It was observed that increment in pitch has most impact on rise of cutting forces. Also, longer the distance of array of dimples is from the cutting edge, lower the values of cutting force. Smaller the size of microdimples, larger the cutting forces generated. This study summarized the performance of micro-texture cutting tool with non-texture cutting tools while machining AISI 1018. Experiments were performed by changing the texture parameter based on estimates derived using the Taguchi method. Following valid conclusions were drawn from the research. The pitch of the textures is found to be the most influential process parameter. Smearing or adhesion of mild steel is lesser in texture tool as compared to the non-texture tool. Micro-dimple surfaces having smaller size dimple have exhibited lower amplitude of vibration as compared to texture tool. Texture surfaces having larger size dimples. Thank you.